Hello. In the last few classes, we looked at translational systems, whether it's in the horizontal case as shown here, or as shown here, or here. And then we looked at the vertically deflected system as shown here. And then we saw that whether you measure from the undeflected spring position or from the SEP, you will have different equations that account for the reference point from which you're taking the measurements. And we did this system here where you study from the undeflected position. You can see that the gravitational terms do feature in the equation of motion, while if you were to measure from the SEP, in that case, with this new coordinate for measurement, you now don't have gravitational terms appearing in your system equation. Okay, so let's now extend this kind of an analysis in the same way of looking at a system, breaking it down into its components, and then defining the forces that connect the components of the system, and then defining the equation of motion. Let's now extend that to torsional loading. What is that? So if you have, for example, in this automotive case, you have an engine and there's a drive shaft, which is transmitting power from the engine, which is in front, to the rear wheels. So now this drive shaft is experiencing torque that is being generated by the engine, and that torque has to be transmitted by the shaft to the rear differential, which will then provide the torque to the wheels, right? That's one case. If you have a motor and you have some load that it's powering, so this here is your motor, and it's powering some device that requires rotational motion. So this shaft again here will have some kind of a torque or a torsional loading that it's experiencing. So gone ahead and drawn a shaft where one end is experiencing a torque of tau1 and the other end is fixed, perhaps welded to some metal structure that is rigid and immovable. Okay, just imagine this. You have on your right hand, you're holding the right side of this shaft and you're holding it fixed, and on the left side with your left hand you are providing this torque tau1. Okay, so considering that this here is a shaft that is flexible, that torque that you're applying will then cause, let's say that we are measuring from some point here, you're causing that surface over here to rotate by some angle theta. Let's say I'm marking that as shown here. This is rotating by theta. And what happens if you were to just look at the point axially on the other face, that is this point here, because it is fixed, then it has no rotation, right? And so this point here has no rotation, this point here has a rotation of theta. And if you were to look along the points axially from here till here, you can say that this will be experiencing a increasingly reduced amount of rotation. Okay, so what I've shown here is this here is the position of points axially from this face to this face, and this one is rotated by theta based on this torque here, and this one is fixed, so there's no theta. And along this axial line that I've shown, these arrows represent how much rotation is happening. Okay, so this is one way of modeling the shaft as it deforms under torsional loading. Okay, again, I've gone ahead and sketched this out as an equivalent model that represents the same system where you're now capturing the rotational inertia of this shaft entirely using this one disk, where this disk is experiencing the same torque tau1, and we show that this disk here is rotating by theta. And then there are torsional springs and dampers that are used for modeling how the system will behave. Okay, of course, the torsional spring is going to capture the elastic deformation, which is how this shaft would spring back to its original configuration when this torque is removed, and the torsional damper is modeling all the losses. So the heating that happens in this shaft, any kind of sound or creaking, all of these things are modeled using the torsional damper. Okay, so this is an equivalent model. And let's now look at how these torsional dampers and springs will be transferring the torque. So gone ahead and written some notes and sketched these out as the three cases. Now, the reason I'm doing it this way is because it takes some time to sketch it in a good visual representation. But in general, we can think of three cases. One case where one end is fixed, as we discussed, and the other is experiencing a twist that causes some θ1 rotation. The other is where uh, both faces experience a twist, in this case in the same direction. So one is θ1, the other is θ2. And third is where they both experience twists, but they are in opposite directions. So one is in this way and the other is in this way. We're going to discuss these in detail. This system can be modeled as one disk that is experiencing torsional loading, such that there is θ1 twist here, and there's a torsional damper and a torsional spring of Ct and Kt coefficients respectively. Let's look at the spring. So the spring is going to create a resistive torque given by tau s is equal to Kt times θ1. And what the spring is experiencing is going to be a torque of this tau s, which is as defined now. Remember that this theta is a measurement, while this here is the torque. Why are they equal and opposite in direction? That's because this torsional spring is massless, and so the net result of this will be equal to 0 only when tau s on both ends are equal and opposite. Of course, since this end is experiencing tau s due to that load torque, effectively the disk over here would experience the reaction torque in the opposite direction. Okay, so we'll see that in an example, but right now I'm only drawing the torques that are experienced by the spring. And similarly for the damper, you have tau d is equal to Ct θ1 dot. It is based on the first derivative of theta, the angular deflection. And here again, it would be experiencing tau d in this way, in the same direction, and it will be equal and opposite across the damper. So this here is the first case. Now let's look at the second case. In this case, we have both phases experiencing twists in the same direction. Let's look at one axial line here. So this end is experiencing θ1, this one is experiencing θ2. Effectively, along the line connecting the net result of that deflection, you would have this kind of deflection along the shaft, but you can now think of it as this region here is simply the rotation of the entire shaft, right? Even though this is rotating by θ1 and this is rotating by θ2, this much is the rotation of the entire shaft. It's not really the twist. The twist, though, is going to be θ1 minus θ2. So if I say if θ1 greater than θ2, the twist is equal to θ1 minus θ2, which is essentially this much. Okay, take a moment to understand that this part of the shaft is just rotating, and then this here is a twist that the shaft is experiencing. So now in this equivalent representation, the torsional spring is going to experience θ1 minus θ2, and the damper is going to experience θ1 dot minus θ2 dot. Okay, and so for that idea, where θ1 is greater than θ2, we would then have tau s is equal to θ1 minus θ2 times Kt. It would be in the direction of θ1, since that is what is greater. And this here is how you'd represent tau s. Similarly, in this case, you have tau d square theta 1 dot minus theta 2 dot times ct. Of course, the above one is if theta 1 greater than theta 2, and this here is a separate assumption that theta 1 dot is greater than theta 2 dot. Um, Again, the direction is going to be in the direction of the larger theta 1 dot in this case. So it's tau s, sorry, tau d, and then tau d here. Okay, let's look at the third case. Now in this case, if you were to look at the axial line, one end is rotating in this direction, and the other one is rotating in that direction. And in terms of the net twist in this shaft, can you think about what that would be? I hope you can see the parallels with the translating spring and damper system. We have net twist in this case would be theta 1 plus theta 2. So the twist is going to be theta 1 plus theta 2. And in this representation now, the spring would have to counter theta 1 plus theta 2, creating a net restoring torque tau s of kt times theta 1 plus theta 2 is acting in the direction of, well, it would be in the same direction as what you see with the angular deflections. Okay, previously it was in the direction of whatever was greater. Now in both cases it would be along that deflection that is shown. So this here is tau s, and now in the third case, sorry, for the damper, you have tau d is equal to ct times theta 1 dot plus theta 2 dot, and again it's along the same direction of for both ends. So this here is tau d. Okay. So in this case, in the left case, it's very straightforward. This tau s is directly along the theta 1, and because the other end is fixed, it's going to have to be equal and opposite. In this case as well, tau s is along the deflections, and it happens to be this way because it is experiencing twist in opposite directions. In this case, is a little special. If theta 1 is greater than theta 2, it'll be aligned according to theta 1. So in case of, well, I think this arrow was drawn in error. It should be this way, theta 2. Okay, so this tau s in the spring is going to be along theta 1, and it would be resisting along theta 2. Okay, so in all of these cases, what's being shown is what the spring and the damper are experiencing. The masses would be experiencing the reaction torque. So it would be tau s here in this direction and tau s in this direction on the connected bodies. Okay, so I guess we can write that as a note. So as I mentioned, we can consider this as just an extension of the previously discussed idea with linear springs and dampers. So in this case, you can think of it as, for the case 1, it's like you have a spring and a damper, and one end is moving by some x, and the other end is fixed. In this case over here, you have a spring and damper, but now one end is moving by x and the other is moving by y. And the third case is where you have them moving again by x and y. In this case, they're going in opposite directions. So these are effectively the three cases that we've just discussed. In this case, fs would be equal to kx. The equivalent over here is tau s is equal to kt theta 1. And fd is equal to, in this case, cx dot. And above it was tau d is equal to ct theta 1 dot. Here, fs was equal to k times y minus x, with it being tensile if y is greater than x, and it being compressive if x was greater than y. in which case the force would be K times X minus Y. And Fd was C times Y dot minus X dot if Y dot was greater than X dot. On the right side for case 3, it was Fs being equal to K times X plus Y and Fd being equal to K times X dot, sorry, C times X dot plus Y dot. Of course, this would be in tension regardless of the value of X and Y based on the direction that is chosen. Okay, so this is how you can relate what we're now studying for torsional systems with what we looked at for linear translating systems. With that, let's study this system over here. So effectively, you have a representation of this system where you have two discs. You have a torsional spring here, a torsional damper connecting the disc 1 to disc 2, and also a torsional spring connecting disc 1 to disc 2. And there's a spring between disc 2 and this rigid wall as well. Was written here that there's a mass that is suspended from the disc over a spring whose other end is wound tightly over the disc. So that means that there's like this string that is wound tightly over the disc, which means there won't be any slipping. So if this end of the disc were to rotate by theta 1, then how much would be released over here? It would effectively be the arc length, right? So if this is theta, the arc length would be r theta, correct? You have a circle, you have an arc set up by theta, then this length over here would be r theta. Right? That's the arc length. So if it were to rotate by theta, then r theta would be the amount of string that's released over here. And that is essentially how much this end of the spring would move down by, assuming theta is in this direction. If theta was in the other direction, that is in this direction, then this end of the spring would move up by r theta. Okay, so think about how you're going to solve this. Of course, in these kind of representations, you always assume that the center of the disk is fixed because modeling torsional systems as a shaft. And so these centers can be considered to be fixed. Take a moment to pause and first define a reference system, visualize how the system is going to behave, and then go ahead. Do you think there will be a difference if you measure from SEP versus from the undeflected position? Yes, there is a spring that is vertically aligned, in which case this spring will hold a static deflection that will cancel the gravitational force of this mass. And similarly, these torsional springs can also hold static torsion that will cancel out the gravitational forces from this mass here that's trying to go downwards due to gravity. If you're confident, you can write that at SEP, deflection of linear and torsional springs will counteract gravity. And with that, you can then safely ignore the gravitational terms. After this, we'll also do the case where we do not make this assumption, and then we account for how much is the static torque and deflection in the spring, and then we see that it'll all cancel out. Okay, so let's define theta 1, theta 2, and some, let's say it moves by y, this mass m. In this case, J1, J2 are the moment of inertia of these disks. It essentially accounts for the rotational inertia of that object. Okay, so we're measuring theta 1, theta 2, and y from SEP. And let's define a direction that is convenient. So you can choose it in any way. I'm going to choose it as shown here. So from let's say SEP, we're measuring theta 1 in this way. And from SEP, we're measuring theta 2 in this way. And let's say from SEP, we're measuring Y in this way, downwards. Okay, so you can now look at defining all of the torques and restoring forces in the spring and damper. So in the torsion spring, let's say we start with the leftmost. It would have tau s being equal to kt1 theta 1, right? Because one end is fixed, the other end is rotating by theta 1. If you had to do kt2, you would have tau s. Let's now name this tau s1, this tau s2, would be equal to kt2 times what? In this case, both the thetas have been defined on the same direction. So we then have to make an assumption. So let's say theta 1 is greater than theta 2. In which case, you essentially have that this side is moving by theta 1 more than this side. And because of that, this spring is going to be experiencing tau S1 in this direction and this direction. So this disc will experience a restoring torque in this direction. It's the opposite of this direction. And this one will experiencing a restoring torque in the same direction as theta 2, which should not be surprising. Okay. For KT3, you have tau S3 equal to KT3 times theta 2. We also have torsional dampers. In this case, you have CT setting up tau D is equal to CT times theta 1 dot minus theta 2 dot if theta 1 dot greater than theta 2 dot. And the direction will be in the same sense as what we just discussed for the spring, torsion spring. We also have linear spring K. In this case, is the force Fs. It's going to be equal to K times R theta 1. So this is moving down by R theta 1. This is moving down by Y. I'm assuming that R theta 1 is greater than Y. And there's going to be, so if this side is moving down more than this side, it will be in compression. For the linear damper, you have Fd is equal to C times just Y dot. It will be in compression. So we've kind of defined the magnitude of all the torques and forces. Let's now sketch the free body diagram. I'm just gonna create a copy of this. It is difficult to draw in real time, so that's why I've been pausing and recording myself drawing it. Instead of recording myself, just sketching these things. Okay. So we have everything we need for the discs. Then let's also do the mass. Okay. Based on the directions that we've been defining, the torsion spring KT1 is going to resist theta 1. So it's going to be in this direction as tau S. So this here is tau S1. It's opposing theta 1. What's the next one? Tau S2 is in the direction of theta 1 inside the spring, and so it's resisting this. And this here is tau S2, and that is the reaction. We also have tau S3 is resisting theta 2 alone, so you have tau S3. Okay, then we have the torsion damper, that is CT. It's in the same direction as spring as we discussed. It's always a simplification that that we have the same direction sense. So we said here there's theta 1 greater than theta 2. Here we said theta 1 dot greater than theta 2 dot. And so the restoring torque will also be in the same direction. So we have tau d. Okay, what else? We have the linear spring. So in this case, that spring would be experiencing compression, and the resulting reaction would be, so spring is experiencing compression. Now the reaction of that would be opposed to that. And so this here is Fs, and we would have Fs as shown between this disk and this mass. So what is here that everything we drew before this were torques. Well, now we have a force. So in a sense, since we want to make use of the same, whether it's torques or forces, if you're writing an equation, it will have to be forces equal to forces or torques equal to torques. So in this case, we'll have to convert this force into a torque based on the moment arm length from the center from which we are taking the moment. So I'll describe that as we do the free body diagram to kinetic diagram representation. Okay, so that was the force. Now we also have the damper that is experiencing compression, and the reaction of that would be in this direction on the mass. So we have Fd here. Those are all of the internal forces restoring. We also have external forces. So there is tau 1 of t, you have tau 2 of t, and you have F of t. Notice how all of these internal forces that we drew, so forces and torques, they all depended only on the direction of theta 1 and theta 2, not on the external forces. In this case, we chose theta 1 to be in this way and theta 2 to be in this way, which is why we got these results. If we had chosen theta 1 to be in the other direction, we would get negatives wherever theta 1 was appearing in this relation here. Okay. With that, we have the free body diagram. You can also do the kinetic diagram. The kinetic diagram, you're only capturing inertial forces and moments. So in this case, you have, due to the moment of inertia, you will have J1 theta 1 double dot in the same direction as this. So that is what I show here as J1 theta 1 double dot. Similarly, you have J2 theta 2 double dot because we had theta 2 in this direction. Now here's Y. So we will have, in this case, My double dot as a force. Okay. So for the first disk, if we were to do the sum of, in this case, moments of the free body diagram about its center is equal to the sum of moments in the kinetic diagram about its center, O. Let's say that we pick a particular direction that we like. So in this case, let's say we do it in this direction as positive. You now get tau S1 plus tau S2 plus tau D plus tau 1 of t. So I picked all of the moments. And now here's the part where a lot of people make mistakes. They just write plus Fs. In reality, this here's a force. All the others were torques. So you have to obtain the moment about that point O. All of these torques, they are acting on the entire body, while this force is acting at a point that is at a distance r away from the center, which is why you're taking this moment. So now this moment will be r cross F. So you have your palm aligned along r such that you can rotate your hand towards this direction of the force, which will result in a direction like this. So the same direction as what has been shown here. So this will be plus r Fs. All of this is on the left side. This will be equal to. Now we have this in the opposite direction to what we drew, what we chose as positive. So it's minus j1 theta 1 double dot. Okay, now if you were to just substitute the values of everything that we defined, go ahead and do that as an exercise. I will write down the final answer. Write it as all I've done is I've gone and substituted the values of each of these from what we defined above. And then I rewrote it in decreasing order of the derivatives. First for theta 1, because it started with theta 1 double dot, then theta 1 dot, then theta 1, and then theta 2 dot, and theta 2, and we have y. Why are all of these on the left? Because these are the system variables or the states which represent how the system is going to behave. On the right hand side is the input to the system, that is the torque that is acting. Tau 1 of t is an external input to the system. Okay, that was for the first disk. Now for the second disk, you have the same result, or the same approach. Let's say I take this direction as positive. I would then get, sorry. So you have tau S3 and everything else is negative. So tau S3 was positive, everything else, that is tau S2 minus tau D minus the external, that is tau 2 of t, is equal to, and in this case there is also in the opposite direction of what we chose as positive, so you have minus j2 theta 2 double dot, and again substituting the values and then rearranging the terms, I get j2 theta 2 double dot plus ct theta 2 dot plus, you get kt3 kt2 theta 2 minus ct theta 1 dot minus kt2 theta 1 is equal to tau 2 of t. Finally, for the mass, you have, while previously we were looking at moments, you're now looking at forces in the free body diagram. Let's say that we choose along the downward direction as positive. What are the forces we have? We have Fs plus F of t, the external force, minus Ft is equal to my double dot. If you now rearrange this and substitute the values, you get my double dot plus cy dot plus ky minus kr theta 1 is equal to f of t. This becomes your equation of motion. So the third one, there's the second one, and this here is the first one. Why do we have three of them? That's because this system is a 3 degree of freedom system. You have variables theta 1, theta 2, and y to represent the system at any instant of time. Given the initial conditions of theta 1, theta 2, and y, and knowing these external torques and moment forces, you can then define how the system moves based on these three equations. Okay. As you recall, in the very beginning, I said that we will discuss the case where we aren't sure if we can neglect gravity, right? So throughout these, when we were doing the free body diagrams, we didn't include the gravitational force of mg. And the reason is because we knew that the static deflection in this spring and these torsional springs will be counteracting gravity. And so those terms would cancel out. Let's say we're not sure of that and we want to go through the entire process. So if we want to verify if we can neglect gravity, at SCP. So essentially, I'm looking to find out what are the static forces that exist and moments that exist. So let's start with a case where we measure from the undeflected. Okay, so this is now the case where there are no external forces. We're measuring from the undeflected position. So let's say this here is undeflected. Okay, undeflected spring positions, and it moves to this point at SEP. So it is rotated by some theta static 1. Similarly, this one is rotated to this position here, defining that as theta static 2. And similarly, from the undeflected position, this mass has moved down to the SEP by some delta static. Okay, what's important to note here is that at the SEP, because static, it means that these damper elements will not be doing anything since there is no velocity, whether it's theta dot or y dot, they are equal to 0 by definition for static equilibrium, right? That's the meaning of static, is that there is no velocity. So that's why I have grayed out the dampers since velocity is 0 at SEP. Defining theta st1, theta st2, and delta st as the deflection from the undeflected position of the spring, all these springs, to the SEP, which is where gravity would be counteracted. Okay, so let's now sketch the free body diagrams. I'm going to do an alternate representation where I show the free body diagrams as disks now, just so it's possible for me to draw it in real time. So this here is disk 1, this here is disk 2. Then we have this mass here. So disk 1 is going to experience restoring torque due to this tau, this spring and this spring. And what are the values of that restoring torque? Well, it depends on theta st1 and theta st2. So let's first define that. So if let's say theta st1 is greater than theta st2, that says this one is rotating more than this one, the net twist is going to be theta st1 minus theta st2. And so you then have tau st, in this case tau st2 is kt theta st1 minus theta st2. You have tau st1 is equal to kt1 theta st1, and tau st3 is kt3 theta st3. Um, then we have the force as Fs being the force is going to counteract gravity, but effectively there's going to be equal to k times r theta st1 minus delta st. Okay, so we have the magnitude of all the restoring forces and torques. We can now sketch the directions. So first, theta st1 is going to counteract this because one end is fixed, so it's acting in this way. So this here is tau st1. What about tau st2? Is going to counteract the greater of them, so that is theta st1. It's counteracting that, so it's here tau st2. And it's going to assist with theta st2 so that the net twist is reduced, right? So it's going to be, as shown here, is tau st2. What about tau st3? It is resisting theta st2, so that is here is tau st3. Sorry. Next, we have Fs. That is going to be equal to this value here. I guess we didn't really define whether it's in tension or compression. It would be, so if this is moving down more than this moves down, then this would be in compression. And so if it's in compression, this is how the spring experiences the FST. So the mass would experience it in the opposite direction. But okay, that is how the that would be the case where this here is the magnitude of the spring force. So this would be compression. Sorry. If r theta st1 greater than delta st. Okay. So the spring is in compression. The net reaction on this mass would be downward. So here's how you have Fst, and you have this as the reaction on the disk. Are we forgetting something? Well, you will have gravitational force here. That's the whole point of this analysis right now. You have mg acting in this way. This disk here, as I mentioned, center is fixed, so there would be some gravitational force acting on this, but whatever support exists is going to cancel that out, so we can neglect that. And the important thing is that there'll be no kinetic diagram because at SEP there is no angular or translational acceleration. So we have at SEP the net moment of FBD for disk 1, this would be equal to 0. So that means tau st1 plus tau st2 plus r fst is equal to 0. That means I've basically chosen this as my positive direction. If you were to now substitute the result, substitute the magnitudes that we defined over here, you will then obtain kt1 theta st1, kt2 theta st1 minus theta st2 minus k delta st minus r theta st1 times r is equal to 0. Why is that this times r? That's because this here is a force at a distance r away, so the net torque is r fst. So I wrote it in this way. Well, I guess I should write it in this way. Plus k times r theta st1 minus delta st. It's plus because if you take this moment, it will be the same direction as everything that we've been drawing as positive. So this here is one relation. This two, again, we have the same. So we do this positive. So you have then that tau st3 minus tau st2 is equal to 0, giving us a relation as kd3 theta st2 minus kd2 theta st1 minus theta st2 is equal to 0. The second relation at SEP, this is what happens. And for the mass, you then have mg plus fst is equal to 0, giving you mg plus what we had here was k times r theta st1 minus delta st is equal to 0. See the third relation? All of that was just the analysis for what's happening at SEP in terms of the net static deflection. So we have this relation here, and this relation. Let's now look at the case from SEP when you're taking measurements. Okay, so to keep it consistent, I'll create a copy of this. And now we're measuring from the SEP. It's no longer grayed out. It does work. Because we're now looking at measurement from the SEP as what did we have? We had theta 1, we had theta 2, and we had y from SEP. So effectively, we're going to repeat these same steps. We now have to look into each of the springs and dampers again. So now let's look at this spring, torsional spring here. So you have tau S1 is equal to KT1 times what is the net deflection? You will have theta ST1 plus theta 1. Tau S2 is KT2 times what is the net deflection? You have theta ST1 plus theta 1, and here you have theta ST2 plus theta 2. Now if I have that theta ST1 plus theta 1 is greater than theta ST2 plus theta 2, and you'll have this as your net result. Okay, that's just, we're repeating the same steps, except now the measurement is from here, right? We're looking at the net deflection, okay? Finally, we have tau S3 as KT3 times theta ST2 plus theta 2. A similar vein to the above, we have tau D is equal to, in this case, CT theta 1 dot minus theta 2 dot. Is because these two are constants, and so when you differentiate them, it goes to 0, essentially stating that there is no velocity at SEP. Then you have for the spring, F spring is equal to, you have R times theta st1 plus theta 1 minus, you have delta st plus y. There's a net deflection. Multiply this by k if essentially this much is greater than delta st plus y. That's basically saying that this is going more than this, which means it's in compression. Finally, we also have Fd is equal to C y dot. It's going to be in compression for positive y dot. Phew, that's a lot. I'm now going to copy these because I'm lazy. Then I'm going to update the free body diagram. So we have you will have tau S1 acting opposed to this. So you have this here is tau S1 as previously sketched. Now you have this here is tau S2 for this consideration. And that's the reaction that I just sketched here. Now this here is tau S3. It's opposing theta st2 plus theta 2. It's tau S3. Don't forget that we had external torques. So we had tau 1 of t, and we had, I believe in this direction, we had tau 2 of t. We also had that force that was in this direction as f of t. Here we have fs. This was mg. Now let's add the damping forces. So you have fd. This one is in compression, which means it's going in this way for the damper. The reaction on this mass would be in the upward direction as fd. Here we have fs. And then we also have the torsional damping, which is in the same direction as the torsional spring. So we have this based on our assumption. Here's tau d, and here is tau d. So all of these were from the free body diagram. Previously, we didn't have to draw the kinetic diagram because it was at SEP. Now, however, because it's no longer at SEP, we're measuring from SEP, there is going to be inertial forces and torques to account for. So we now have kinetic diagram here on the right. It has to be in the same direction. So this here is J1 theta 1 double dot. This here is J2 theta 2 double dot. And then we have My double dot. Why do we not have theta st1 double dot? That's because theta st1 is a constant. So theta st1 dot would be 0 and theta st1 double dot would also be 0. That's why this is only featuring theta 1 double dot. Okay, so these are the free body diagrams and these are the kinetic diagrams. That's a lot of work. Just to ensure that we are sure that the gravitational forces cancel out, and the key to that is that these terms will go to 0. So let's now apply ourselves to relating the free body diagram to the kinetic diagram. So for the disk 1, I'm going to write tau S1 plus tau 1 of t plus tau S2, and we have plus RFS plus tau d is equal to minus J1 theta 1 double dot. Sorry. And sorry. If you now substitute the values, I'm gonna write the whole thing down. Should get okay. So all I did was substitute the values from here. From here. Now, what you do is you notice that you have a relation here that is equal to 0. So I'm going to just copy that there. And let's see what happens. So this was the relation that we had found. So kt1 theta st1, kt2 theta st2 minus theta st2 plus kr kr r theta st1, well, this is theta st1, I missed that, minus delta st is equal to 0. So I can essentially cancel this out. That's how it cancels out. And then you get as your final answer, I move this to the other side. We have that was a lot of work. But this here is an equation of motion for the first disk. Let's now compare this with what we had found earlier. This is what we had found already, as accounting for static torques and, well, actually, instead of accounting for, I should say, confidently asserting that the static torques and deflection forces in the springs would cancel out the gravitational forces. This is what you obtain as equation of motion, and it is identical to this. Let me verify if it's identical. Well, I guess this one, as it goes on the other side, there should be a minus term, so I forgot that. But with that, it is now identical. You can do the same for disk 2, and for the mass, you should get the exact same result. You will write down tau d plus tau s2 minus tau s3 plus tau 2 of t is equal to j2 theta 2 double dot. And then as you do that, you will find again terms that cancel out based on this relation. And the end, the equation of motion that you obtain will be the same as what you had obtained here. So when you can see that the springs are acting against the gravitational force, then the static deflection will cancel out that gravitational force. Okay, so in general, if you're confident about that, you don't have to specifically verify using all of these relations, and you can just write down what we did in the first attempt. I hope that makes sense. Again, if you're not sure about something, email me, set up office hours, and I will clarify anything that you have questions about.